Okay, so we just got done looking at sample problem 11.6, and now we're ready to go into our next section in chapter 11, which is looking at curvilinear motion, looking at and identifying position, velocity, and acceleration. And basically, this is going to be any type of motion that isn't in a straight line. It's going to be actually over a curve. Now, the classic example and what we're going to look at here is going to be projectile motion. Now, for those who, and you all have had the statics already, these are going to be familiar to you. Now, projectile motion has actually two components to it. So it's going to have a horizontal direction component to it, and then we're also going to be looking at the vertical component of it. So before we kind of look at these equations, I want to go underneath here and hopefully as a familiar illustration. Let's say we're looking at a ball, okay? And a ball is thrown, and it's instead of going in a straight line path, it's actually going to, curve something like this. So this would be the start, and then I'm going to call this like the middle-ish, all right? And then this is going to be the end. And what we have going on here, for instance, if we show the velocity of that ball being thrown, it would be at some angle. So this would be, if you would, our original velocity. That would mean that there's going to be a x component at whatever angle this would be to, horizontal or vertical. So this would be VOX. And then we would have a VOY. Okay. Now, horizontally, we're going to look at each one of these. And when I call it the component of the motion, that vertical component here is this one going straight up and down. And then this is going to be the horizontal component. So X and Y respectively. Okay. Now, when we look at that horizontal component, we're going to treat it like it would be going in a straight line. Okay. So it would just be going horizontal, horizontal, horizontal. And we're also going to qualify it as having uniform motion. So that means that we're going to assume that this velocity is going to be going at a constant rate until it gets to, it's kind of bugging me, this is a little short, until it gets to its final value over here. Okay, so VOX is going to be that horizontal component, but it is going to have a constant velocity value. Okay, so once we possibly can calculate it, then that's going to remain the same throughout, the amount of time that it takes us to get to the other side here. Okay. Now, the vertical component, on the other hand, because this is a ball and it's being thrown, and we're assuming that we're going to be on Earth, it has the acceleration of gravity acting on it all the time. Okay, all the time. So it is affecting its value in that vertical direction. So as this goes up to its highest point, this vertical value, if I'm here, it's going to continue to diminish because for each second that goes by, it's slowing down because gravity is acting on it. Okay, so our velocity original in the y direction gets shorter until it's nothing here. Okay, so in this case, it's only moving vertically, and it's only moving vertically here. And this value remains the same each time, for all of these positions. Okay. Now, once it gets to the top here and that vertical velocity has been exhausted, it just means that VOY is equal to 0. It kind of like stops at that very instant because it's like changing direction. Okay. And then what happens when we get over here, we still have our vertical component of our velocity, whoopsie, VOX. But now the only thing that's different is the direction of velocity vertical is now it's going to start speeding up as it goes down. So this value here, if it's the same one across, is going to be now same magnitude, but just going in the opposite direction. Okay. And then down here, we're going to have our highest value back to whatever it would have been at this point. So our velocity in the y direction, see, not y, our velocity, OY, is going to be constant acceleration. And then that's going to be due to gravity, right? Due to gravity. So if we look back at the last section that we looked at, whenever we're trying to figure out something on the horizontal direction, we're going to be in a constant velocity mode. And whenever we're trying to figure something out in or identifying the motion in the vertical direction, we're going to then be in the constant acceleration mode. Okay. So best thing to do here is to kind of go back and we're going to look at the equations for each one of those directions. And that's what I have on this slide right here. So for projectile motion, when we are in the horizontal direction, we can see here that the acceleration in the x direction is equal to or assumed to be 0. Okay, we're also not going to take air drag into account for the problems that we're looking at here. Okay, so our x value at any point along that projectile, the velocity in the x direction is going to be the same as it was on the original. So if we look back over here, this original value is going to be all the way along that horizontal direction. Okay. And then if we want to know where we're at any instance in time in terms of position, you can see that the familiar equation, we're going to add in any offset distance from the origin, and then we're going to add to it the velocity that we had in the x direction times however many, segments of time that we're interested in. So that's going to be our horizontal. Again, that's uniform motion or constant velocity / 0 acceleration. The vertical direction then, because of the fact that there is an acceleration in the y direction, and it's going to be due to gravity, okay? So in this case, when we have that y value for the velocity, the y component, we're going to take that original y value, and then we're going to add the acceleration times time, okay? Now, right now, I don't have the negative in here, but when we're dealing with things that are, accelerating due to gravity, then this would become a negative, value because of the direction of the acceleration. And then we're going to have the distance in the y. Again, familiar equation, because this is going to be the uniform acceleration. And then this is going to be the velocity in terms of distance. Okay. So again, if we look back underneath, they're really going to, and I added this to my equation sheet, projectile motion. This is going to be my horizontal direction. This is going to be my vertical direction, my acceleration, my velocity, and my distance, accordingly. And then acceleration, velocity in 2 cases, and then our distance in the y direction. And then I just did our little illustrations here, like we saw on the other one. Okay, so we are going to be doing sample problem 1110 to kind of use the relationships that we just looked at and apply them to a projectile type of a problem. Okay. Just want to kind of leave this up in case anybody is marking that down. I'm going to grab the problem statement for sample problem 1110. This is found on page 672. Okay, I'm going to take this away now and go back underneath this guy. And here is the problem statement for problem 1110. So over on the left-hand side here, we have a projectile is fired from the edge of a cliff that's 150 meters from the bottom of a cavern. Its initial velocity is 180 meters per second at a 30-degree angle, as we see there. Neglecting air resistance, find the horizontal distance from the canyon to the point where the projectile strikes. So from here, we want the horizontal distance to where it lands down here. And then we also want to get what is the greatest elevation above the ground that is reached by that projectile. So what is this point from here down to here? Okay. So what we want to do is we want to, kind of get started here and identify what we're given and identify the variables that we, have and then what we want to find. So this is going to be sample problem 1110. Okay, again, it's on page 672. And what we are given, and I'm going to do a little illustration here just so that we can relate our variables to what the illustration has or what the figure has. So I'm going to start here with our origin. This is where they're identifying the origin for our problem. And this is going to be the point where that projectile takes off. Okay, so from the horizontal, this is going to be 30 degrees. We know that the VO here is 180 meters per second. And just kind of drawing, if you would, kind of its trajectory so that from here to where it hits the ground, okay, this is going to be the distance x that we want to find, okay? We also know that this is 150 meters above the ground. And I think I called that y for my problem. Now, something that the problem wants to know is the problem wants to know at the top, at its highest elevation, okay? I'm going to kind of draw a little dimension out here. What is that highest point? I'm going to call that YF, okay? That's going to be its highest elevation. Okay. Now, that's kind of the problem so far. So we know that VO is equal to 180 meters per second, as we have stated there. Because this is a projectile and we're on Earth, we know that we have acceleration of gravity acting, and we know that to be negative 9.81 meters per second squared. In the problem, we won't put the units, okay? We also know that our Y here is 150 meters, okay? And we want to find, for part A, we want to find what is that distance x, okay? From where we launch our projectile to where it actually lands at the bottom of the cavern. And then part B is what is our YF for that highest elevation, right? Now, because this is a projectile, we have those two conditions going on, simultaneously. We have horizontal and we have vertical, okay? So we want to find what those horizontal and vertical components are to get started, and then we're going to be looking at the separate motions. So components. I am going to draw them up here. You guys have had plenty of component work. You guys had me for statics, or most of you have had me for statics. This is going to be my VOX and my VOY, okay? So step number one is going to be components of VO. So just so we can see it on the screen here, I'm just going to draw a quick little coordinate system. I've got my 180 meters per second, 30 degrees. This is going to be my VOX, and this is going to be my VOY. We have a right triangle that's created here. Now remember, we don't float our VOY out here or our VOX up here. They have to start and they are applied, you would, at the tail of the 180 meters per second. So to calculate our actual values for our X and Y components, our VOX horizontally, this is going to be the cosine function, okay? So VOX is going to be equal to 180, which is the hypotenuse, times the cosine of 30 degrees. Okay, cosine because it's a side adjacent, divided by the hypotenuse, and then solving for that side adjacent. So this number should come out to be 155.88 meters per second. I'm going to leave the units off. And then our VOY, it's vertical here. We would kind of see it out here. We would imagine it out here, but it would be the 180, our hypotenuse, times the sine of 30 degrees. Okay. So our VOY, we multiply those out, should get 90 meters per second. Okay. So these are going to be the values that we will be using corresponding to the horizontal and the vertical motions. Okay. Everybody get those and kind of remember components and such. The chat box out so I can see it. Only 2. Oh, tacos. Okay. All right. So now that we have the components, our second step now is we want to look at the vertical motion, okay, and the horizontal motion separately. I just happened to do the vertical motion first. I think that's how the book did it in that order. So I kind of went along with that. So vertical motion. And we know that to be constant acceleration, okay, due to gravity. So that means it's going to be a negative 9.81 meters per second squared, right? Okay. So if that's the case, kind of coming back over here, vertical direction here, these are going to be the equations that we're going to use because this is the constant acceleration equations, you know, in terms of the y. So I'm going to start off with my velocity in the y direction. It's going to be equal to, so that would be my v final as a function of time. And it's going to be the VOY or the original y plus the acceleration due to gravity times t. So if I expand that out, it's going to be 90 meters per second. Okay, so that's my VOY 90. And then I'm going to have plus AT. Now, we know that the acceleration is a negative 9.81. So don't forget, you're going to do plus negative 9.81 times t. Okay. So that means I can say that Vy is going to be equal to 90 minus 9.81 t. Okay. And I'm going to leave it in those terms, that velocity in the y direction as a function of time. Oops, Chris, let's see. Oh, it was in radians. Yes, that can happen. Yeah, be careful. If you're in radians, you start getting weird numbers. Yeah. I've done that more than once. Okay, so that's our first equation. So we did the velocity in the y direction as a function of time. Now we're going to get the y distance as a function of time and velocity. So this one, we're going to say y is equal to, and y is going to be equal to the velocity original y times t plus 1/2 the acceleration of gravity times time squared. Now, something I didn't add was the VO or the XO here or the YO. I didn't put it on right now because our origin is at 0 here, and this is where we're starting. So from our origin where we have our YO starting, it's at 0. So there isn't an original distance. So I'm going to go like this to expand that out. So Y is equal to YO plus, this is 0 because our origin is right here at the start of the projectile. Okay. So if I insert my values here, okay, I'm going to get my 90 times t, and then this is going to be plus 1/2 times negative 9.81 times t squared. So then my y is going to be equal to 90t minus 4.905 t squared. And we'll leave it just like that. And then the third one is going to be the velocity of y in terms of the distance. And that's going to be this last one right here. This is going to come in handy when we want to find what the distance is that it elevates to. So this one we're going to do as well this time. So we've got vy squared is equal to our original y value squared plus 2 times a y. Okay. And that's going to be equal to 90 squared, that's our VOY, plus 2 times negative 9.81 times y. Okay. So we square this, and then we're going to multiply these out. So my VY squared is going to be equal to 8,100, 90 squared, minus 19.62 y. And that's my third and final vertical motion equation. So I'll give you a second before I move on here. Now we're going to start looking at the horizontal motion. So we took care of our vertical. Now we're going to look at our horizontal. Okay. So step 3 is going to be horizontal motion. And when we look at horizontal, kind of bringing my little sheet back here, we know that our acceleration is equal to 0. Our x velocity is going to be constant. And then our function of our horizontal distance is going to be the original offset plus the velocity original times the time that we're interested in knowing. So this is just x. I crossed out, I had made a mistake. I used a pen. I didn't have a pencil at the time. That's okay. All right. So as we look here, we know that ax is equal to 0. We know that our velocity OX is going to be the velocity along any time in the x direction. And we know that to be 155.88. It's this right here. Okay. Again, leaving the units off just to keep it simple. And then our x value, okay, is going to be equal to any offset from the origin plus velocity original in the x direction. And it's constant, right? It's going to be the same number. So whether you do VO or VX, it doesn't really matter, times the time. So that means that we would say, because this goes to 0, we would say x is equal to 155.8, because that goes right there, times t, right? So horizontal distance, we can calculate at any given time multiplied by the constant velocity that we're seeing in that x direction. All right. So we've got our motion, if you would, defined in both directions. Now, what we want to find is what is the vertical distance or what is the time that it takes to get to over here. We want to find out what x is. So we need to know, okay, what is the time does it take to get there? Now, it's kind of hard to know if we want to go along that x-axis, we have to know a time. So that doesn't help us. And we don't know how, we don't know how far that's going to be. But what we do know is we do know in the y direction that we're starting out with that 90 meters per second going up. So we want to know, okay, if I throw it up at that point, okay, this offset distance, how long is it going to take to go from that point and just drop down? Because that's going to be the time that it takes to get over here. Because those two things are going on at the same time. But how far does it take to drop from where we're at right here to there? Okay. So to do that, we can use, so this is step number 4. This is going to be looking at that vertical distance. Okay. We need the time t for how long it's going to take to drop. So the equation that we used earlier is going to be the second one. So the y is equal to, okay, 90t. That's how much we throw it up. And then this is going to be its effect on that gravity has on it and how much, and we've got the time there. So we're going to say 90t minus 4.905 t squared. Okay. Now, we know that the y distance that we're going to fall or drop, we look back at our problem. If we're here and we want to get down to here, the y distance that we're going to drop is 150 meters. Okay. So over on the left-hand side here, this y value is going to be negative 150 meters. It's negative because it's going in a downward direction from the origin that we identified. So this is going to be 90t minus 4.905 t squared. Now I'm going to move my 150 to the other side to set this equal to 0. Okay. So it's going to add 150 on both sides. So I'm going to have 90t minus 4.9005 t squared plus 150. I'm going to take the m off. I keep adding the m's to the ends. Okay. Now you can see here that I have this equal to 0, right? That distance as a function of time, and because we've got the square and the t here, this is in a quadratic form. So if I want to put it in the official quadratic form, I want to put the square first, minus 4.905 t squared plus 90t plus 150. We can find t using our quadratic calculator. So I'm going to just kind of point at this and say quad form, right? Because now I can go to my calculator and find what that value of t is when my x becomes 0 or my y becomes 0. So I am going to share my other screen, which has the calculator on it. So you could put this position 1 here, but I've already got my A, B's, and C's figured out. So this is my A, B, and C. So to save a little bit of time, I'm not going to worry about the equation on top. So my A here is going to be a negative 4.905. So that'll go there. My B is positive 90, and my C is 150. So the two values of time that I get here, the negative value is like before I even start. So that one's not going to be an option. So the time when my position, my y value is 0 is 19.88 seconds. Okay, 19.886. So that's going to be the number that I'm going to write down here. So 19.886 seconds. Okay, that is going to be the time. Back over here. And sorry, I've got to reshare screen. Okay, so the 19.886 seconds is going to be the amount of time that it takes to go from that origin when we send off the projectile to when it actually touches the ground, when y is equal to 0 or the negative 150 meters. Okay. So now that I know that time, I'm going to put my little cloud around there, because again, this is not a final answer. Now that I know this time, I can figure out what my x distance is, right? So if I go back to my horizontal motion, actually just above here, I can calculate my x value by using 155.8 times the time. That's the time that we just calculated. Okay, so I'll know how far out I'm actually traveling. So 5 is going to be my x distance overall, right? And if we go back to our little diagram here, it's from the origin over to here. Horizontally, that's the distance that we can calculate now, is equal to 155.8 times the 19.886 seconds. Leave the S off, sorry. Not a bad habit, it's a good habit. Okay, so my X value here should be 3,999.8 meters. And I believe that the book rounds it up to 3,100, okay? This is the X distance, which is, I believe, part A. Okay. Just gonna hold here for a second, making sure that everybody has the same values I have. Okay, perfect. Yep, you got the same number I did, William and James. Thank you, thank you, thank you. All right, so now that we have that was the first part. Now the second part of our problem, remember, it wants to know, pull this back in here, what is the highest elevation from the canyon floor? Okay, what's the highest elevation from the canyon floor? So what we're going to do is we need to kind of divide this into a couple sections here. So there is the Y, the 150. There's the highest elevation, but then there's this Y here, okay? And I call this Y up. And it's the Y value from where I start my projection or my projectile, and it goes to the very tippy top right here. We also know that at that very tippy top position, our VOY or our VY is equal to 0. I'm going to say VY. Our VY is equal to 0. It's like changing directions. So that's the very highest that it's going to be before it starts going right back down. So that very instant between going up and going down. Okay. So the equation we're going to use for this one is going to be the one that we developed. It was the third one here for the vertical motion. We're going to use the Vy squared is equal to 8,100 minus 19.62. And this is the Y up. Okay, that's going to be that little distance right there. Right. So I am going to simply, this is going to be my step number 6. We're going to calculate that first distance. Okay. So Vy squared is going to be equal to that 8,100 minus 19.62 Y, and I'm going to call this Y up. So it's that little section to the top of that projectile from where it was originally launched. Now, because we know that this is going to go to 0, because at the very tippy top there, remember our Vy component of the motion is equal to 0 because it's changing directions essentially. So that means that this is going to be 0. It's going to be equal to 8,100 minus 19.62 Y up. So our only unknown in this equation is the Y up. So pushing my 8,100 over to the opposite side. Both sides become positive. Solving for the Y up, I'm going to divide both sides by 19.62. My Y up should come out to be 412.8, and it would be meters. Okay. Now, it still isn't my final answer, so I'm not putting a box around it, putting a cloud around it. Looks like Jason, and hopefully, did Jack get that? Was that just now? Maybe not. Let you guys get that. And now that we know that portion, we can say that the highest elevation is going to be equal to, okay, y plus y up. Okay, y plus y up. So now we know both of those. So our y final, the highest elevation, is going to be y plus y up, which is equal to 150. I'll add the meters this time, plus 412.8 meters. So our y final from the bottom of the canyon floor is going to be 563 meters. This is a final answer. I'll let you guys finish that up. Just want to get maybe one or two confirmations on the same numbers that I have. Then we'll do a little review and then we'll look into our last problem for the night. Did anybody get to that point where you got the same answer as I did, hopefully? Or any questions?
Can you show me the top where we first started with the graph? Just so I have all the points labeled right?
Yep. Oh, 563. Thank you, James. This one right here?
Yeah.
Yep. Yep.
Yeah, I just want to.
Good, Chris. Okay, I also got 563. Excellent. 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 Thank you, Isaac. Thanks, Christopher. Yeah, and then this is the illustration with all the variables. Okay. All right. So I'm going to stop the recording right now, but I'll keep this up so that if you do need to finish, you can.